I'm Sujani, faculty in physics at Institute of Aeronautical Engineering, Hyderabad. Today we are going to discuss about communication in optical fibers. So we have been discussing about fiber optics for the last 3 lectures. We have already covered the principle, construction and working of optical fiber. We have seen the expressions for acceptance angle and numerical aperture. And in the last class, we have seen different types of optical fiber based on the mode of propagation, also based on the refractive index of the core, and also the type of materials used. And today we are going to discuss in detail about how communication happens in an optical fiber, and we will also see some applications of optical fiber. So let us see the brief outline of how we are going to discuss the topic today. First, we will discuss about attenuation. Attenuation is nothing but the losses that occur due to transmission, during transmission. And also we will see how transmission happens in an optical fiber communication and also the applications. So first let us define what is attenuation. Attenuation is the loss of power suffered by the optical signal as it propagates through the optical fiber. When we have discussed regarding an optical fiber, we have seen how the signal is being launched into the optical fiber and how signal propagates through the optical fiber. So as the signal propagates through the optical fiber, whatever losses that happen to the power or to the signal, we are calling it as attenuation. It is also called as fiber loss. In other words, we are also calling it as fiber loss. So signal attenuation is defined as the ratio of input optical power into the fiber to the optical power output at the other end of the fiber. So if we are considering an optical fiber, we will have the core and we have a cladding. So we will launch a signal in single mode. We have seen it travels in a straight path. So we will consider a single mode. So here we are giving the signal. This is the input and this is the output. Here we get the output at the other end. If this is the optical fiber, we are calling this is the core and this is the cladding. So when the signal is put inside the optical fiber, we call it as the input and this is the output for the signal. So it is defined as the ratio of the input optical power Pi to the optical power output P0. Now the attenuation coefficient, which we denoted by alpha, per unit length, we are going to measure the attenuation coefficient of the signal per unit length and it is given by 10 by L log to the base 10 Pi upon P0. So Pi by P0 we are calling it as a signal attenuation. So when we are writing the formula for the attenuation coefficient, which is denoted by alpha, alpha is equal to 10 by L log to the base 10 Pi upon P0. So L here represents the length of the fiber. L is the length of fiber. And this is measured in decibels per kilometer. So the attenuation coefficient, because we are measuring the attenuation coefficient per unit length, so we are denoting it by decibel per kilometer. So whenever we have to calculate the attenuation coefficient, we use the formula. Knowing the values of Pi, the power input, the power output and the length of the fiber, we can very easily calculate the attenuation coefficient. Now when it comes to attenuation, there may be different types of attenuation at different regions. So the total attenuation, if you have to calculate in an optical fiber, it will be the sum of all the losses. The losses due to different areas. Maybe it may be due to absorption or it may be due to scattering or due to bending. So the total attenuation or the total loss is always equal to the sum of all the losses. Then the optical losses of a fiber are generally expressed in decibels per kilometer. We have already discussed this. Now for a fiber, the losses are wavelength dependent. It always depends upon the wavelength of the signal. And the value of the attenuation factor depends greatly on the fiber material, means the material which we are using to make the optical fiber, and also the manufacturing tolerances. While manufacturing, what is the tolerance that it can withstand? These two are the factors that affect the attenuation factor or the attenuation coefficient. Now, the typical fused silica glass fibers we use today has a minimum loss of 15,015 nanometer, means 1550 into 10 power minus 9 meter. Nano means 10 power minus 9. So, whatever glass fibers we are using, typical fused glass fibers we use today, they have a minimum loss. After taking care of all these attenuation factors, so the minimum loss that occurs is 1550 into 10 power 9 meters. So this is the minimum loss that occurs for a signal. Now the mechanisms through which this attenuation takes place. The first one is the absorption loss. Second is the scattering loss. And third is the bending loss. In bending loss, we have two types. The micro bending, where the bending is very small, and also the waveguide losses, where the bending may be more. So, we are going to discuss each type of loss in detail. The first one is absorption loss. Absorption loss is uniform throughout the fiber. Means the same amount of the same material always absorbs the same fraction of light at the same wavelength. We said this attenuation depends upon the wavelength. Now, when we are talking about absorption loss, absorption is due to the absorption of the signal or the light. So, the same amount of the material absorbs same fraction of light at the same wavelength. We are sending the signal at a particular wavelength. So, at that particular wavelength, the material absorbs the same fraction of light. So, how do we understand that? If you take 3 blocks of the same type of glass, each of 1 centimeter thick, means we are considering 3 blocks like this, each of 1 centimeter thick, made of the same material or the same glass. All the 3 will absorb the same fraction of light when the light passes through them. So, this is a block of glass of 1 centimeter thick. So, whatever fraction of light this absorbs, this also absorbs the same, and this also absorbs the same. But absorption is also cumulative. So, what do we understand by cumulative? It depends on the total amount of material the light passes through. So, how do we understand this? Now, if the absorption is 1% per centimeter, we have calculated or we have observed that the absorption of light is 1% per centimeter of this block. Then it absorbs 1% of the light in the first centimeter. So, in this here, 1% of the light, I have sent input is 100%. So, 1% of the light is being absorbed in the first block. Now, no doubt, the second block also made of the same material, same thickness, it also absorbs 1%. But it absorbs 1% of the remaining 99%. That is the difference here. We mean by cumulative, taking everything into cumulative. So, it absorbs 1% of the light in the first centimeter and 1% of the remaining light in the next centimeter and so on. So, this also absorbs 1%, but here 1% of the remaining. So, when we calculate 1% of 99% and whatever is left of that 1%. So, that is how we calculate the absorption losses. Now, in absorption loss, we have something called intrinsic material absorption. What is this intrinsic material absorption? It is caused by the interaction of the propagating light wave with one of the major components of the glass that constitute the fiber material. So when we have seen the structure of the optical fiber, we have seen the core is generally made up of glass and it is surrounded by cladding usually made up of plastic. Now what we are understanding here is, so when the light passes through the core, there will be interaction of this light with the intrinsic material. Intrinsic material here is the glass of which the fiber is made. That is a major component. So there may be an interaction and because of that there may be a loss. That is what we are calling it as intrinsic material absorption. And these losses represent a fundamental minimum to the attainable loss and can be overcome only by changing the fiber material. So if you have to minimize this loss, so when it is made up of a particular material and we have seen for a given material, for a given thickness, the amount of absorption is fixed. Now, if we have to minimize the losses, if you are taking one material and the amount of attenuation or the absorption is more, then to minimize it, you will only have to change the material. When the material changes, then the absorption also varies. So, an example of such interaction of the light wave with the major component of the glass is the infrared absorption band of SiO2, silicon dioxide. So, when we have the signal that is traveling, the infrared absorption by SiO2, that is a typical example for intrinsic material absorption. Now coming to extrinsic impurity ion absorption. So extrinsic impurity here means it is caused by the presence of minute quantity of metallic ions. When we say extrinsic, we say it is impure. Whenever there are small impurities that are there in the material, then we call it as extrinsic impurity. So when there are impurities such as Fe2, Cu2 or copper or chromium or the hydroxide ions from water that are dissolved in glass. So we are taking the major component is glass, and when this glass has some impurities like iron, copper or chromium or the hydroxide ions from water, when these impurities are there and when the light makes an interaction with these particles, then there may be absorption, which we call it as extrinsic impurity ion absorption. Now the second one is the scattering losses. Scattering losses occur when a wave interacts with a particle in a way that it removes the energy in the direction of the propagating wave and transfers it to other directions. So here in scattering losses, what is happening? The wave will interact with the particle in its way. When the wave is propagating through the optical fiber, if it is interacting with any other particle, so some amount of energy is removed and it is transferred to other directions. Here it is not absorbed. The light is not absorbed, but it is sent in another direction. That is why we call it as scattering. So the propagation of the light on its way, it may interact with some particles that remove the energy and scatter it in different directions. So that type of loss, we are calling it as scattering loss. However, the distinction between scattering and absorption doesn't matter because light is lost from the fiber in either case. Whatever the signal input we have given is lost. Either in absorption it is absorbed, in scattering it is lost to the surroundings. It is scattered in different directions. In both the cases the signal is lost. What only thing we are understanding is the loss is occurring due to absorption or due to scattering. So in scattering also we have two types of scattering. One is the linear scattering and the other is the non-linear scattering. So we will discuss these two scatterings now. Linear scattering and non-linear scattering. So for linear scattering, the amount of light power that is transferred from the wave is proportional to the power in the wave. So whatever input power we have given, so more the power input, more the amount of light that is scattered. So For linear scattering, the amount of light power transferred from the wave is proportional to the power in the wave. And it is also characterized by having no change in frequency. So the wave that is scattered, there is no change in frequency. Whatever the frequency of the wave is, the scattered wave also will have the same frequency. And on the other hand, for nonlinear scattering, it is accompanied by frequency shift of the scattered light. So when you see the scattered light, it is always having a change in frequency, which we call it as the frequency shift. So this is the main difference between linear scattering and nonlinear scattering. In linear scattering, when the wave interacts, what happens is there is no change in frequency of the scattered wave. But in case of nonlinear, the frequency of the scattered wave changes. So the nonlinear scattering is caused by high values of electric field within the fiber. So when this fiber is subjected to high values of electric field, then this nonlinear scattering occurs. And this causes significant power to be scattered in all the direction, forward, backward and sideward directions. So whenever there is a loss due to scattering, it may occur in different directions. So it is scattered into the surroundings in different directions. Now this is one graph which depicts the types of losses or the attenuation. So we are plotting a graph for wavelength, lambda, versus attenuation. We have seen that attenuation depends upon the wavelength. So we have taken the wavelength range from 800 to 1800 and we are trying to observe what type of scattering occur at which wavelengths. So the wavelengths we are measuring in terms of nanometer. So what we understand here is different type of scattering. The first one we are going to see is the Rayleigh type of scattering. A scattering which we have discussed just now, named after a scientist, Rayleigh. We will discuss about it again. Okay, so this curve shows the Rayleigh scattering, means at different wavelengths how the attenuation is occurring. Means what it shows here is at lower wavelengths the Rayleigh scattering is more, but as the wavelength increases, the Rayleigh scattering goes on decreasing. That is what we have understood about wavelength dependence. Now, if you see the other type of scattering which is shown by this violet line, the loss of spectrum is at a peak at this particular wavelength. And in infrared absorption, what we are seeing, this is the line. This is the line that shows the infrared absorption, this one. So what is happening here is, it is increasing as the wavelength increases, the infrared absorption increases. And in ultraviolet region, because when we talk about wavelength, we have the ultraviolet region and also the infrared region and also the visible region. So here in ultraviolet, it is very less and it is almost becoming minimum. And there are other types of losses also. So we can understand with the help of this graph the dependency of attenuation or wavelength. Now we will discuss about Rayleigh scattering. Rayleigh is the name of the scientist. So this is a type of linear scattering. Linear scattering, here we understand that there is no change in frequency after the scattering. That is, the scattered wave will have the same frequency as the incident wave. Now Rayleigh scattering is named after the British physicist Lord Rayleigh, and it is the main type of linear scattering. And it is caused by small scale. That is, small when we say it is compared with the wavelength of the light wave. Inhomogeneities that are produced in the fiber during fabrication process. So when we are manufacturing an optical fiber, if there are any inhomogeneity, homogeneous means uniform throughout. If there are any homogeneities in the fiber during the fabrication process, so the scattering that occurs due to these inhomogeneities, we are calling them as Rayleigh scattering. And also they have to be very small when compared to with the wavelength of the wave. And what are the examples of inhomogeneities are glass composition fluctuations. Means whenever we are using a glass, if there is a minute change in refractive index of the glass, so then it becomes inhomogeneous. And also there may be fluctuations in density. Density here we talk about the mass per unit volume. So whenever these type of inhomogeneities are there occur during the fabrication process, and the scattering that happens due to these inhomogeneities, we are calling it as Rayleigh scattering. And this Rayleigh scattering accounts for about 96% of attenuation. So scattering is more in this case, Rayleigh scattering, it accounts for 96% of attenuation. So if the attenuation has to be reduced, then we need to focus more on Rayleigh scattering. Means during the fabrication process itself, care has to be taken to minimize the inhomogeneities. If the inhomogeneities are less, then the scattering is less, because we see here that 96% of the attenuation in optical fibers is due to Rayleigh scattering, and Rayleigh scattering is due to the inhomogeneities. Now the third one here is the bending losses. So in bending losses, we have two types, the macro bending and the micro bending. So macro happens when the fiber is bent into a large radius of curvature relative to the diameter of the fiber. When we compare the diameter of the fiber with the radius of curvature in which it is bent, if it is very large, then what happens? We call it as macro bending. And if you see here, this is the macro bending loss. So this is the fiber we are taking, optical fiber. So this is the diameter. So you can know the radius of curvature of this. And if it is bent in a large radius of curvature, then we have these macro bending losses. And these bends become a great source of power loss when the radius of curvature is less than several centimeters. So when this is less than several centimeters, then what happens? The bending is, or the loss is very high. And macro bend won't cause significant radiation loss if it has large enough radius. So if the radius is very large, then the loss due to macro bending is very less. The significant radiation loss is very less when it is having a very large radius. Now coming to the advantages of optical fibers. Advantages of fiber optic cables over copper cables, means the conventional cables that we use for communication. So the first one is greater bandwidth. Bandwidth here represents the range of frequencies through which the signal can be sent. Now copper cables were originally designed for voice transmission and have a limited bandwidth. So copper cables have limited bandwidth, but fiber optic cables provide more bandwidth for carrying more data than copper cables of the same diameter. If you are taking two cables, one copper cable and one optical fiber, both of the same diameter, but fiber optic cables can carry a large amount of data because it has a very high bandwidth when compared to copper cables. And the second one is faster speed. So fiber optic cables have a core that carries light to transmit data. So when we are talking about a fiber optic communication, whatever signal that has to be sent, light is used as a carrier wave to carry the signal. So what happens? This allows the fiber optic to carry the signals at speeds that are only about 31% slower than the speed of light. We know the speed of light is 3 into 10 power 8 meters per second. And when we are using this light as a carrier for the signal, so obviously it has to travel, the signal also has to travel at this speed, but due to certain losses, the reduction in the velocity or the speed of the signal is only about 31% slower than the speed of light. faster than copper cables. When you compare with the copper cables, it is very fast. Then there is no signal degradation or less, minimum signal degradation with fiber cables. Means the loss of signal due to distortion is very less in optical fiber cables. Now, longer distance communication. So, with the help of optical fibers, we are able to carry the signals to very large distances. They can carry signals much farther than the 328 foot limitation for copper cables. If you are talking about copper cables, that has a limitation of 328 foot. So, but this limitation is not there for fiber optic cables. For example, we are talking about 10 Gbps signal mode fiber cables can carry signals almost 25 miles. So when we are talking about copper cables, the limitation is 328 foot, but 10 Gbps optical fiber can carry signals almost 25 miles. Then the actual distance depends upon the type of cable, the wavelength and the network. So the signal can be transmitted, but the actual distance that it can travel depends upon the type of cable we are using and also the wavelength at which the signal is being propagated and the network that is being used. Now, better reliability. So, these optical fibers are immune to temperature changes. Immune means with the variation in temperatures, there is no much significant effect on the signal that travels through the optical fiber. So, severe weather and moisture, all of them hamper the connectivity in case of copper cables. If you are talking about copper cables, whenever there is a change in temperature, so when it becomes hot, these copper cables may sag, they expand. Okay, and due to severe weather or due to moisture, also there may be connectivity issues. But optical fiber is immune to all these changes in temperature, changes in weather or moisture. And the next one is fiber do not carry electric current. Because optical fiber, when we are talking about, we are using light as the carrier to carry the signals. So it does not carry electric current. So it is not bothered by electromagnetic interference. Means the disturbances that are caused due to electromagnetic radiations. So these radiations, where the disruption, we call it as electromagnetic interference, that may disrupt the data transmission. Whenever we are transmitting the data, these signals may interfere and then they may interrupt the data. But here, in case of optical fiber, it is immune to electromagnetic interference. And then it is also not prone to fire hazards, like worn out copper cables. So what happens when the copper cables are worn out? They are exposed and they may become potential areas for fire hazards. But in case of optical fiber, we are taking enough care. So we have seen it during the structure of an optical fiber. What we have, the core is the main thing that carries the signal, but we also have the cladding and then the protective layer, and then we give strength to the material, and then the silicone coating and also the outer layer of the sheet. So we are taking enough of care to protect these optical fibers or to make them sturdy. So thinner and sturdier compared to copper cables. So fiber optic cables are thin, but they are sturdier. But fiber optical cables are thinner and lighter in weight. They are thin. Because they are thin, they are light in weight, but sturdier when compared to copper cables. Then fiber optics can withstand more pull pressure than copper and is less prone to damage and breakage. If you see that way, you may think that copper is a metal, but still when we are using it under the pull pressure, okay, so what happens here is fiber optic cable is less prone to damage and breakage when compared to copper cables. Then comes to flexibility. After reliability comes the flexibility. So future media converters make it possible to incorporate fiber into the existing networks. So wherever they are copper cables, still they are going to replace everything in the future with fiber optic cables because of all these advantages. And then the converters extend UTP Ethernet connections over fiber optical cables. So whatever connections we have, Ethernet connections, internet connections, that are done using a fiber optical cable. Then modular patch panel solutions integrate equipment with 10 GB, 40 GB and 100 and 120 GB speeds to meet the current needs. So what we are doing and provide flexibility for the future needs. So in the future, whatever speeds that are required is going to increase and increase because the amount of data that has to be transmitted increases. So what happens here is even if the data speed also can be increased with the help of these optical fibers. Now the last one is lower cost. Although some fiber optical cables may have higher initial cost because the fabrication process, because to draw very thin fibers, it may cost more. But because of the durability and the reliability of the fiber, the total cost will be lower. Because you need not replace them frequently, their durability is more, they are sturdier. So what happens here is the cost the incurred is very less when compared to the conventional cables. And cost continue to decrease for fiber optical cables and related components as technology advances. So as the technology advances, so we may have more and more developments where the cost may continue with more new materials that are being used. So the costs may decrease further. Now coming to the optical fiber communication. How communication happens? First part we have seen. If at all the signal is traveling through an optical fiber, what are the losses that occur? And what are the advantages of using this optical fiber over copper cables? Now we are going to see how communication happens in an optical fiber or using an optical fiber. So there are three parts. The first part is the transmitter. Second is the optical fiber. And the third is the receiver. So the first one is the transmitter. If you see here, this is the transmitter section from where the signal is being transmitted. And this is the optical fiber which carries the signal that is input into the optical fiber is carried with the help of this optical fiber, and this is the output of the signal. The signal is received by the receiver. This is the receiver. So we have the electric input signal at the transmitting section, transmitter, and then the light being propagated through the optical fiber. And this is the receiver which receives the signal, or we have the electrical output signal. So these are the three main parts in fiber optic communication. So we are going to discuss one by one in detail. Now the transmitter. First the transmitter we are going to look at. It includes encoder, drive circuit and light source and couplers. So when we are talking about the transmitter, this block is the transmitter. This is the transmitter. So in a transmitter, what we have, the first thing is the encoder. So where the input signal is given. So after the encoder, we have the drive circuit and then the light source and then some couplers we have here to couple the signal to the optical cable. So this is what we have in a transmitter, the encoder, the drive circuit, then the light source and then the couplers or the connectors. Then the receiver. The receiver consists of light detector, amplifier and decoder. So in a receiver, this is the receiver block. We call this as the block diagram for optical fiber communication. So the first part is the transmitter. The second one is the optical fiber. This is the optical fiber. And the third one is the receiver. So we have seen what we have in a transmitter. Now in a receiver, what we have is a light detector and then an amplifier to amplify the signal and a digital or a decoder, and we get the output. So we will discuss first, after seeing the block diagram, we are going to discuss how the signal is going to be transmitted through these blocks. So what is the main principle of optical fiber communication? So it basically converts an electrical signal into an infrared light signal. And this signal is transmitted through the optical fiber. And at the end of the optical fiber, it is reconverted into an electrical signal. So we have seen three blocks. One is the transmitter, then the optical fiber, and then the receiver. So what is the function of the transmitter? It converts an electrical signal into an infrared light signal. And this light signal will pass through the optical cable. And at the other end, we have the receiver, which will convert it back to an electrical signal. It will convert the light signal to electrical signal. Now, working step by step. So, first thing we had is the encoder. What is the function of an encoder? It is an electrical circuit where the information is encoded into binary sequences of zeros and one. Binary means two, either a 0 or a 1. So that is what we call as binary. Whatever information that is fed or that is given as input is encoded into binary sequences of zeros and ones. So in a light wave transmitter, each one, if you are talking about one, it corresponds to an electrical pulse. There is a pulse if it is 1. And if it is a 0, it is absence of pulse. There is no signal or there is no pulse. So this is what happens in an encoder. It is an electric circuit where the information is encoded into binary sequences of zeros and ones. 1 means the presence of an electrical pulse and 0 is the absence of pulse. Now this binary data, we have converted into binary sequences. It comes out as a stream of electrical pulses. And these pulses are converted into pulses of optical power by modulating the light emitted by the light source. We are using a light source. And with the help of this light source, these electrical pulses are being converted into pulses of optical power by the light source. And these electrical pulses are used to turn on the light source on and off rapidly. So when it is high, it is on. When it is 0 or it is off. So how these electrical pulses will turn on and off the light source. Then we have the laser drive circuit, which will modulate the intensity of the laser light, which is encoded with the encoded digital signal. So the modulation occurs, means whatever signal that is coming in the digital form, that is being modulated with the intensity of the laser light. Now, it converts the incoming electrical signal into a form that will operate with the light source. So now what is happening here? The laser drive circuit is driving it. How? The incoming electrical signal into a form that will operate with the light source. Now comes the couplers. Couplers in the transmitter couple the transmitted light signals with the fiber. So whatever we have, the light that is encoded, with the help of the drive circuit, we are coupling it, and we are making the light to pass through the optical fiber now. So we need couplers. So the couplers will couple the transmitted light signals with the fiber. And the digital optical signal is launched into the optical fiber. So the function of these optical couplers will be to launch it successfully into the optical fiber cable. And now the optical fiber acts as a waveguide. We have seen in the beginning that optical fibers are nothing but channels for transmission of waves, or it acts as a waveguide and transmits the optical pulses towards the receiver by the principle of total internal reflection. We have seen the principle on which an optical fiber works. It works on the principle of total internal reflection. So what we have here is, one is the transmitter block, the second one is the optical fiber block, and the third one is the receiver. So this is the transmitter. So whatever we have seen in the transmitter, the signal is input is given, then it is encoded. We are converting it into a binary sequences, and then with the help of the drive signal, we are driving the signal with the help of the light source, and then with the help of the couplers, we are coupling it into the optical fiber. Now the signal will travel through the optical fiber based on the principle of total internal reflection. Total internal reflection occurs inside the fiber, and then we have the output. So the light detector receives the optical pulses and converts them into electrical pulses. So in the receiver block, what we have is the light detector. So the output that comes from the optical fiber is detected by the light detector in the receiver. It will receive the optical pulses and convert them into electrical pulses. And then these signals are amplified by the amplifier. So what is happening here is the signals that are coming from the light detector are being amplified, and then they are decoded by the decoder. Here in the transmitter, we had the encoder. We have converted it into electrical signals. Now we are converting the light signal into electrical signal. So they are being decoded by the decoder. So this is the block diagram, entire block diagram for optical fiber communication. If you understand this block diagram, the entire process of communication through optical fiber becomes clear. So we will just look at it again. This is the transmitter block. So in the transmitter block, what we have is the coder or the converter. And whatever the digital pulses that are being converted, we have discussed it is high 1 and low 0. So these digital pulses are driven with the help of the driver circuit or the light source transmitter circuit. So this, with the help of couplers, it is coupled into the fiber optic cable. So this is the fiber optic cable. So the signal that comes from the optical fiber at the other end, now it is going into the light detector. So this is a photocell or a light detector. Then the signal is being amplified. So after amplification, what we have is a decoder. So which will decode, which will convert the light signal into electrical signal. So we are seeing here different modes. If we are talking about a telephone, the analog information is being given as input. This is the input. The sound signals may be converted into electrical signals and they will travel through. And when it comes to the other end, again these electrical signals may be travel. The analog output gives us again the sound signals. So the analog information is input here and then the output here. Even in the case of digital information using computers, here this is how the signal is fed in the form of digital pulses. The same process happens, and again from the digital pulses we have the output, digital output for computer. So this is the main block diagram for optical fiber communication. Now to transmit signals to long distances, if we have to transmit the signals to long distances, we use repeaters after certain lengths, because when we are using long cables, there may be practical problems that may be there for laying. So what we do here is, and also there are chances for losses. So we are going to use repeaters. So what is an optical repeater? It consists of a receiver and a transmitter arranged adjacently. The receiver will convert the optical signal into the corresponding electrical signal, and the transmitter will convert the optical signal into electrical signal. So here what we are seeing is, this is the transmitter block, whatever we have seen till now. There is a message or the input signal. We have the modulator, the carrier source and the couplers. Then it travels through the optical fiber. But when it has to travel long distance, we use repeaters. So these are called repeaters or optical amplifier. So in each repeater, what you have is a transmitter and a receiver. So from here, if the signal comes, we have a receiver which receives the signal and then again it transmits. So each optical receiver consists of a receiver and a transmitter. It will receive and again transmit. Again it will receive and transmit. And the other blocks remain the same. This is the main transmitter and this is the receiver. Now what happens after reaching the repeater? The electrical signal is amplified by means of an electrical generator and is sent into the transmitter section. So in a repeater, we have seen we have the receiver and we have the transmitter. So once it is received, it is amplified and then transmitted. So in transmitter section, the electrical signal is again converted back into the optical signal and is fed into the optical fiber. So from here, the last section again, the whatever signal that comes out, it has to travel through the optical fiber. So in the end, from the transmitter here, again it is converted into optical signal and is then traveling through the optical fiber. Now at the end of the optical fiber, the signal is fed into the receiver. And what the receiver consists of? It consists of a light detector, which can either be an ADP, that is an avalanche photodiode, or a pin diode, positive intrinsic negative diode, pin diode we call it. And in a photodetector, the signal is converted into pulses of electrical current, which is then fed to the decoder. So from here it is fed to the decoder, which converts the sequence of binary data into analog signal. Now the binary data is converted into analog signal at the output, near the output, that is with the help of the receiver. Now coming to the applications of optical fiber, where all optical fibers are being used. So the first one is power transmission. Optical fibers are used to transmit power using a photovoltaic cell to convert light into electricity. So we are using an optical fiber to transmit power. And they are also used in military as hydrophones which can be used underwater or for seismic and also for sonar uses. Sonar we know. Sonar is sound, navigation and ranging. So whenever you will have to measure the distances or the depth of oceans and all, we use a sonar. So even in such cases, we are going to use optical fiber. And it is also used as wiring in aircrafts, submarines and other vehicles, and also for field networking. So in all these areas, we are going to use optical fiber. Now fiber optics are used to connect users and servers. So in computers, what we have is there will be a server and there will be a user. So to connect the two, users to the servers, in a variety of network settings, and it helps to increase the speed and accuracy of data transmission. We have already discussed this. If you are using a copper cable, the speed and the accuracy of data transmission is less. But with the help of fiber optics, when we are using it in different networks to connect users to the servers, the speed and accuracy of data transmission is high. Then also in broadcast and cable companies, they use fiber optic cables for wiring, that is HDTV, internet, and then even for video signals. In all these cases, they are using optical fiber. Here we can see a beautiful picture of a fiber optical cable system which is used in internet. Now coming to the sensors. Fibers have many uses in remote sensing. In some applications, the sensor is itself an optical fiber. So an optical fiber itself can be used as a sensors, and where we are going to use the sensors are to measure the strain, the temperature and pressure and some other quantities. Wherever we have to measure the temperature or measure the strain or the pressure, we use them as sensors. They will sense and give us the data. Then extrinsic fiber optic sensors has the ability to reach places which are otherwise inaccessible. See, why we are using them as sensors is there may be some areas where we cannot reach, a human cannot reach. But when we send an optical fiber, the optical fiber can go inside, reach the region and gauge or access the data or sense the data with regard to temperature or pressure. So an example of this is the measurement of temperature inside the aircraft jet engine. So in an jet engine, if you have to measure the temperature, because when you are using an engine, there is a tendency that the temperature may go high, it can get heated up. But we need to know the sensors. Even in cars, we have the sensors which will gauge and tell us the temperature, how hot or how cold it is. So the regions where we cannot reach, we can use optical fibers and sense the data. So one example here is the aircraft jet engine. Then extrinsic sensors can be used in the same way or to measure the internal temperature of an electrical transformer. We know transformers which carry very high electric currents. So in case of electrical transformers also we have to measure the internal temperature. So we use these sensors. Then comes the telecommunication. So optical fiber is used in many telecommunication companies to transmit telephone signals, internet communication and also cable television signals. So we have telephone, television and internet. All these communications can be done using optical fiber. And in some cases, because the bandwidth is very high, we may be using one single optical cable to carry different types of signals. That is also one more greatest advantage of using optical fiber. We call it as many into one. Many signals can be sent through one optical fiber. And unlike electrical cables, fiber optics transport information to far distances with few repeaters. So if we have to transmit the data to very long distances, we have seen that we are going to use repeaters. So with the help of these repeaters, we are able to transmit data to far distances, which is not possible with the help of electrical cables. Then fiber optic cables can carry a large number of different signals simultaneously. So simultaneously you can send different signals through a technique called the wavelength division multiplexing. So we will be dividing the wavelengths, or we can talk in terms of frequency and send different signals through one. Optical fibers are ideally suited for carrying digital information, which is especially useful in computer and cellular networks. So in both the cases, in computer networks and cellular networks also, we are using optical fiber cables. Now coming to medicine, the use of optical fibers in medicine. So medical endoscopes are used for surgical procedures to view the internal parts of the human body. So suppose there is a surgery to be done on some internal parts of a human body. So where with the help of an optical fiber, the surgeon can view what is there inside. No? The physician, it will enable the physician to look and work inside the body without performing the surgery. So it will be a minimum invasion surgery, we call it as. While performing the surgery with a minimum invasion, what they can do is they can send an optical fiber, see the internal parts and then do the necessary surgical procedures. So in medical applications, we have, based on the application, endoscopes are classified into, there are many types of endoscopes. The gastroscope, which we used to examine the stomach, then bronchoscope, which is used to examine the lungs, orthoscope we have, which is used to see the joints, and peritonia, which is used to see the internal organs like liver, gallbladder. Whenever there are problems in the liver or the gallbladder, without making an incision or doing the actual surgery, with the help of these endoscopes, they can make the corrections or give the treatment. And also in ophthalmology, lasers guided by fibers are used to reattach the detached retina. Ophthalmology is related to the eye. So whenever there is a problem with the retina, they are using this to attach or detach retina. When the retina is getting detached, maybe due to old age problems or some other problems, They are using these fibers even to do such things. Then in spectroscopy, optical fiber bundles transmit light from a spectrometer to a substance that cannot be placed inside the spectrometer itself. Suppose when we have to study the composition of any crystal or any material which is found, then what if you cannot keep it inside a spectrometer and then study it? So we will use optical fiber bundles and analyze the composition. And by using these fibers, a spectrometer can be used to study objects remotely. In a remote way, with the help of the spectrometer, we are able to study the objects or the materials. So for more information or for more applications on optical fibers, you can refer to books Engineering Physics by Palaniswamy or Engineering Physics by Gar and Gupta or Modern Engineering Physics by Vijay Kumar and Chandralingam. Thank you. See you again in the next lecture.
Like, share and subscribe. Hit the bell icon for more updates.